Welcome to Mrs. Roberts' Algebra 2 class. This is our second chapter that we're flipping, and we are talking about a chapter on statistics and probability. Today's lesson is on the fundamental counting principle, permutations, and combinations. It is the first video for us. Our objective today is to use the correct statistic to determine the number of events. Here's some vocab that I'd like you to write down. You might want to pause this for just a minute, but this is the vocab from 11.1. One of the vocab words is the fundamental counting principle. It says if there are R ways to do one thing, S ways to do another, and T ways to do a third thing, and so on, then the number of ways to do all of those things at once is R times S times T. We need to remember that these are different things. We're not choosing 5 things from a group of from a group of the same things. We're choosing different things. For example, we're choosing one shirt, we're choosing one pair of pants, we're choosing one pair of shoes, and we're choosing one thing from a set of groups. We could choose one letter or one number for a password. A permutation is a grouping of items in which the order does matter. That's usually considered a ranking, like first place, second place, third place, or an assignment of roles. For example, president is a different role than vice president. Vice president is a different role than the secretary. Anytime that you're assigning those different roles, that's when a permutation is used. We say NPR if you look right over here. Okay? NPR. And that N represents the total number of things in our group, and R represents the number of things that are chosen. They can be the same number, but R can never be bigger than N. And then the funny equation there says N with an exclamation point. That means N factorial over N minus R factorial. And one thing that you need to write down that's not on here is that 0 factorial equals 1. And I know that doesn't make a lot of sense, but there's a lot of statistical reasons for it, and we're not going to go into that today, but there is some reasoning behind it. So anytime you end up with 0 factorial, the answer is 1. Combination is a grouping of items in which the order does not matter. It's NCR, and it's a similar formula. It says N factorial over R factorial times N minus R factorial. Permutation grouping matters. Combination grouping does not matter. Now let me just scroll up a little bit further. That N with the exclamation point, as much as I'd like it to mean that we're excited about math, it means N factorial. And the N factorial says to multiply every integer from 1 up to that number. So for example, if we had 5 factorial, that would be 1 times 2 times 3 times 4 times 5. Which if we multiply that out, 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120. Okay, pause that if you didn't get all of those. Now, let's look at a couple of options, a couple of examples. Jenny has 3 different shirts, 4 different pairs of pants, and 2 different pairs of shoes. How many different outfits could she possibly wear? She can't just throw all 9 of these things into a pile and pick 3 things out. She's not going to want to wear 3 shirts to school. You're not going to want to show up at school without a pair of pants on. You might want to go without shoes, but definitely not without a shirt or pants. So she's going to choose 1 shirt, she's going to choose 1 pant, and she's going to choose 1 pair of shoes. And we want to know how many different ways can she do that. When she's choosing 1 from each thing, so she's got a shirt, and she's going to pick 1 shirt. She's got options for pants, and she's got options for shoes. Right? What that means is we need to think, how many shirts can she choose from? Well, she has 3 different shirts that she can choose from. How many pants? 4 different pants, and 2 pairs of shoes that she can choose from. This is the fundamental counting principle. We are choosing 1 thing from this category, 1 thing from this category, 1 thing from this category. And so we simply multiply all those together. 3 times 4 is 12, times 2 is 24. So she has 24 different outfits that are possible. All right, this next one is one that I want you to try. You go to lunch, you've got one sandwich, one side, and one drink. How many different lunch specials are there? Still a fundamental counting principle because we're choosing one thing from the sandwiches, we're choosing one thing from the sides, and we're choosing one thing from the drinks. All right, pause this, try it, and then check back and see if you got the right answer. All right, sandwiches. How many sandwich choices does she have? She has 3 sandwich choices. Let me try that again. She has 3 sandwich choices. How many side choices does she have? She has 4 side choices. How many drink choices does she have? She has 3 drink choices. So we're going to multiply those 3 things together. 3 times 4 is 12, times 3 is 36. So there are 36 different lunch specials. All right, now we're going to look at an example of the permutation. Bill, Ted, Kate, and Ann want to take turns playing at a video game. How many different orders can they play? Here's the thing. If I play in first place, is that the same, if I play first, is that the same as playing last? No, so this one is one where order is important. Order matters. Which means it's a permutation. So we're going to use the equation for N, P, R. N is the total number of things that we're choosing. Well, there are 1, 2, 3, 4 different people in this group, so N is 4. R is the number of things that, N is the number of things we're choosing from, and R is the number of things that we're choosing. Well, we happen to be letting all 4 of them play, so R is also 4 in this case. And so we're going to look at this equation, and remember it was N factorial over N minus R factorial. So in this situation, that means it's 4 factorial over 4 minus 4 factorial. So that means that's 4 times 3 times 2 times 1 over 0 factorial. But what did I say 0 factorial equaled? Right, it equaled 1. So I have 4 times 3, which is 12, times 2, which is 24, times 1. So I have 24 divided by 1, which is 24 different ways or different orders that they can play in. Okay, all right, got another example for you. Jack, Chuck, and Vin are racing around the block. How many different ways can they finish the race? No ties. Every person's going to get a place, and since we're talking about places, think about what kind of equation is this, or which formula are you going to use? Is it a permutation or is it a combination? Pause it, try it, and let's check back and see how you did. All right, so we said it was a permutation because the order matters. N is the total number of things in our group. Well, there are 3 people in our group, so N is 3. R is the number of things that we're choosing. Well, we're going to give everyone a place. So again, N and R are the same. It will not always work out to be that way. So our formula says N factorial over N minus R factorial. Okay. N factorial is 3 factorial over 3 minus 3 factorial. It's really important that you put parentheses around that and that you do the 3 minus 3 first. So that 3 minus 3 is 0 factorial. 3 times 2 times 1 is 3 factorial. 3 times 2 times 1 is 6. And 0 factorial, remember, was 1. So how many different ways can they finish? 6 ways. Now we could list all of those out, but we're not going to do that here. We're just curious. We just want to know the number of different options that there are. Okay. Now, so suppose you wanted to select 3 people from a group of 7. We have 7 people in our group, so we can know that N is 7. We're choosing 3 of them, so R has to be 3. But we have to decide, is this a permutation? Does the order matter? Or is it a combination? Does the order not matter? Are these 3 people being assigned any roles or any positions or any places? If they get selected first, do they get more money than if they get selected third? It doesn't give us any information like that. So we assume that their order does not matter, which means it's a combination, or NCR. Okay. Now, that formula is n factorial over r factorial times n minus r factorial. And notice this is an example where r is not the same as n. So let's plug things in. So we have 7 factorial over 3 factorial times 7 minus 3 factorial, which is 7 factorial over 3 factorial times 4 factorial. Now, we have to make sure that we write out 3 factorial and 4 factorial before we multiply. 3 factorial times 4 factorial is not the same thing as 12 factorial. I would encourage you to write those out. So 7 factorial is 7 times 3, not times 3, 7, and let me see if I can get my eraser here or not. There we go. Let's see if I can erase this. All right, let's try again. And grab my pen back. Okay. Let's try that again. How about 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. Now let's take a look at this. What can we do here? If I can get my pen to cooperate for me, let me try it this way. Let's pick a different color. Let's go with blue. All right. What do you see here? We have a 4 times 3 times 2 times 1 in the numerator and a 4 times 3 times 2 times 1 in the denominator. I can cancel those because those numbers are going to be exactly the same. Then I look over here. I have 7 times 6 times 5 over 3 times 2 times 1. And I could multiply these things out and divide it by this. But if I think 3 times 2, that's 6. So it could cancel with that. So there are 35 different ways that we could choose a group of 3 people from a total of 7 people. Okay? All right, I want you to try this next one. Pause it when you get done. Pause it when I get done reading it, so that you can try it and see what you think and see if you get the right answer. It says Mrs. Roberts is going to give extra credit to 4 students from a group of 9. How many ways can she give out the extra credit points? Again, we need to ask ourselves, does it matter to the students what order they're chosen in? Probably not, because as long as they're one of the 4, they're going to get that extra credit. So because it doesn't matter, first of all, we know that n is 4. No, excuse me, n is 9 because n is the total number, isn't it? R is 4 because that's the number of people that we're choosing. We said order doesn't matter, so it's N, C, R. Look at the formula. We get 9 factorial over 4 factorial times 9 minus 4 factorial, which is 9 factorial over 4 factorial times 5 factorial. Okay? So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All over 4 times 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. Okay, let's try to change our pen here so we can see what we're doing. Okay. Now, is there anything that we can cancel? Well, yes, I have 5 times 4 times 3 times 2 times 1. And then I have 5 times 4 times 3 times 2 times 1. I can cancel all of those. Now, if we remember, 3 times 2 is 6, so I can cancel those. I could take 9 times 8 times 7 and divide it by 4, but I could also see, oh, 4 goes into here once, and 4 goes into here twice. That leaves me with 18 times 7, which is 126 different ways. Did you choose that it was a combination, and did you get those right? Good. Now, you can do this on your calculator. Unfortunately, I don't have the best calculator to show you this, so I'm going to just tell you on the graphing calculator, if you look under the math key, if you go over 4, it says PRB. And if you have a TI, like a TI 30X, it also has a probability key. They're both, the math and the PRB key are near the second function key, which is in the upper left-hand corner. This PRB, when you look, you will see NPR, NCR, and factorial. And so you could let the calculator do it for you as well. You do need to know how to write these out because I will be asking you how to solve these. All right, let's try a few practice problems. Let's see if you can figure out which ones are which. All right, there are 3 problems here. It says, how many ways can your class select a president, treasurer, and secretary from a group of 5 students? Once you pause this, think about that. Is this a fundamental counting principle? Is it a permutation, or is it a combination? Make your decision, pause it, try the problem, and then check to see did you do it correctly. Okay. First of all, we know we're choosing from 5, and we're choosing 3 things. Okay. President, treasurer, secretary. That is a ranking, so that means that we have to do a permutation. 5p3. So it's 5 factorial over 5 minus 3 factorial. Now, if you figured out on your calculator how to do this, we know that 5 times 4 times 3 times 2 times 1 is 5 factorial, and we have 2 factorial in the denominator, so I can cancel those, and I get 12 times 5, which is 60 ways. Did you get that? Did you write out the ways, or did you figure out how to use your calculator? Okay, look at problem number 2. Jordan wants to choose 4 pieces of candy from a pile of 10 pieces. How many choices can she make? Is this a fundamental counting principle? Is it a permutation? Does the order matter? Is it a combination? The order doesn't matter. Try what you think, pause it, and see. All right. Did you just say that it was a combination because the order doesn't matter? It doesn't matter what order she picks those 4 pieces in. She'll get those 4 same pieces in however she does it. She's not ranking them. She's not choosing her favorite and then choosing her next favorite or anything like that. So n is 10 because that's the total number she's choosing from, and r is 4 because that's the number of items she's chosen. All right, so we have 10 factorial, if we look at the equation, over 4 factorial times 10 minus 4 factorial. Now, 10 factorial, remember, is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's going to get a little long to work out. So I'm going to put it in my calculator. When I put it in my calculator, I need to put the n in first, 10. Then I find the math key or the PRB key, and I select that 10 NCR. And then I tell my calculator what the r is, which is 4. And when I do that, I get 210 different ways that she could choose 4 pieces. All right, we've got this last one here. A password is formed using 4 letters followed by 1 digit. Uppercase letters and lowercase letters may be used and are considered different. How many passwords are possible? Think about this one. Is it a fundamental counting principle? Is it a permutation? Is it a combination? Try what you think, and then pause it, and come back and see, did you get the same answer that I get? All right. I'm going to say that this one is a fundamental counting principle. I am choosing one thing for the first digit, or first letter, one thing from the second letter, one thing from the third letter, one thing for the fourth letter, and one thing for the fifth digit. How many choices do I have for letters? Well, there are 26 letters in the alphabet, but I can use both upper and lowercase. So I have 52. I still have 52 for the second choice, 52 for the third choice, 52 for the fourth choice, and then I have digits. How many digits are there? Right, there's 10, because 0 through 9 is 10 digits. Now, multiplying that out gets kind of long, but we can use our calculator to help us out. It's the same thing as saying 52 to the fourth power, and then multiplying that by 10. When we do that, we get 73,116,160 different passwords. All right. So we're almost done with today's lesson. What you need to do now is to summarize what you've learned and write a question that you have about the lesson. Was there something that didn't make sense? I'll be excited to talk to you about that tomorrow. For those of you that are doing the video, have a great night.